This is how to calculate water pressure. So whether you're talking about a water tower that has the water up 200 feet, or whether you just dive underwater and you're 5 or 10 or 20 feet underwater, this is how to calculate the water pressure on you. It's really easy. The amount of water doesn't matter, whether it's a huge tank or just a narrower pipe or a wide pipe. All that matters is the height of the pipe or the depth that you're swimming underwater. You'll run out of water a lot sooner if this is a pipe flowing down and there's no tank on top, but otherwise, yeah, it's just the height that determines pressure though, and that's ignoring any internal resistance to flow. Keep the pipes wide enough and that won't be much of an issue. Here's how you do it. It's simple enough because 1 cubic centimeter of water weighs 1 gram. So if you have a little cube here, 1 centimeter in all directions, that's 1 gram of water right here. So if you are 4 centimeters deep underwater, or if you have a pipe that's 4 centimeters long, 1, 2, 3, 4, you now have 4 grams of water on top of you. And the area will be 1 centimeter by 1 centimeter, so 1 square centimeter. So it's 4 grams per square centimeter. So the number of centimeters deep you are equals the number of grams per square centimeter. If you're 200 centimeters deep, then the pressure is 200 grams per square centimeter. Or if you have a pipe that's 4,000 centimeters long, then you have 4,000 grams per square centimeter. From there, you can use apps to convert from grams per square centimeters to PSI or kilograms or whatever you want. I just recently learned that you don't have to change your forces or pressures to newtons. You can use KGF, which stands for kilograms force. So whatever grams you have, you can easily convert that to kilograms by moving your decimal point over 3. And that will give you kilograms of force per square centimeter. Then you can use apps to change that to PSI or whatever. But if you don't want to use apps, you can stay tuned and I'll show how to do all the conversions without an app. So you'll be able to convert back and forth from length to volume to area to pressures to PSI to kilograms per square centimeter or whatever. So stay tuned if you're interested, but if you just want to know how to calculate water pressure because you swim underwater pretty deep, this is all you do. For anyone that wants to stay tuned, there's more details right here. First off, if you take the area times your length, the area right here, 1 centimeter by 1 centimeter, times the length, which would be 4, then that will give you the volume. And notice right here, when you multiply your units, meter squared times meter gives you meter to the third. So we have a square and then a linear number, just a meter is a straight line, and that gives you a volume. We can reverse this and take volume divided by length to get our area. Notice here it's meters cubed divided by meters. You subtract your exponent, you'll get meters squared. Here's how we could use it here. For example, we got 4 cubic centimeters, 1, 2, 3, 4, and we'll divide that by our length, which is 4 centimeters. That gives us our area in centimeters squared. So divided by 4 is just 1 square centimeter for the area on the bottom right there. Maybe a little redundant going back and forth there, but I figure it's good to practice to really understand it. This is why I use the metric system instead of imperial, because if you have 4 square centimeters of water, 4 cubic centimeters of water right here, 1, 2, 3, 4, 1 cubic centimeter equals a gram. So now we know we have 4 grams of water right there pushing down on 1 square centimeter. So our pressure will be 4 grams per square centimeter. Typically people convert that to newtons, so I'll show how to do that on the next page. But what's more important is I'll show how to convert this to PSI, just easy steps, step-by-step baby steps. Okay, so for the example here on the conversions, let's take a tall tower, a couple hundred feet, approximately 60 meters. First off, convert that to centimeters because that's super handy because 1 cubic centimeter of water is a gram. So we can use that to get the pressure. Don't worry about the volume of the tower. All that matters is the height. Kind of like you don't have to worry about the volume of an ocean that you're swimming in. All that matters is the depth that you're underwater. Length will be 6,000 centimeters. I just converted meters to centimeters. Area will be 1 square centimeter right there. Length times area gives you your volume. 6,000 centimeters times 1 square centimeter, 1 by 1, gives us 6,000 cubic centimeters right here. And the handy part about a cubic centimeter is that that's easily translatable to grams. That means we have 6,000 grams per square centimeter. Leave your decimal point over 3, and you get 6 kilograms per square centimeter. I prefer to leave it there for pressure because then you can convert kilograms to pounds to get PSI. But in physics terms, like on an app, they'll give these terms in newtons. So once you get your kilograms, you have to multiply by 9.8 or 10 if you want to round it, and that'll give you newtons. 60 newtons, because 6 times 10 is 60. 60 newtons per square centimeter is the result that apps will give you on pressure. I'm going to leave it as kilograms so I can change this to pounds. 6 kigs right here. 1 kig equals 2.2 pounds. That means we have a total of 13 pounds right here per square centimeter. And then what that means though is we're mixing our imperial units with our metric units. So let's go ahead and convert this square centimeters to square inches. So then we can have our pounds per square inch. This looks like it could be complicated, but it's not when you take this in super easy or small baby steps. Let's take a square inch. 1 square inch, so it's 1 inch by 1 inch. 1 inch equals 2.54 centimeters as the conversion. So if this was 1 inch per 2 centimeters, then that means that this 1 inch would have 2 centimeters, so you divide it right down the middle. It'd be 1 centimeter from here to here, and then another centimeter from here to here. But it's actually 2.54 centimeters, so let's move it over just a little bit because it has to go into this twice with a little left over. So we take our 1 centimeter, that equals 2.54 centimeters per inch. Notice there's no squares here or cubes or anything like that. This is all linear. So centimeter divided by centimeter cancels, you end up with 0.39 inches. Now we know we got 0.39 inches here times 0.39 inches here, 0.39 squared. Right there gives you 0.16 inches. So yeah, when you square a number that's smaller than 1, in this case we're squaring 0.39, you're going to get a really small number because it's a small number times another small number. If this was a cube and we were doing volume instead of area, this would be a cube going across this way, a very badly drawn cube right here. And you would have 0.39 inches across, 0.39 inches deep, 0.39 inches up, so it'd be 0.39 inches squared, cubed, and then that would give you your volume in cubic inches. So what we have here is 13 pounds that I got from the kilograms per 0.16 square inches. That is our pressure right there. But when dealing with these fractions or these units, you typically want 1 in the denominator. So I could just say divide 13 by 0.16, but I'm going to explain why. We want this denominator to be 1, so how do you turn it into 1? You divide by itself. So multiply by 1 over 0.16, then this becomes 1 square inch right here. Just bring your units down. Whatever you do to the denominator, you have to do to the numerator, and vice versa. If you alter the numerator, you have to do the same to the denominator. So 13 divided by 0.16 right there gives you 81. That's a big jump from 13 to 81, but that's a pretty small number right there, 0.16. So now we got 81 pounds per 1 inch squared. You could say 81 pounds per inch squared, or you could say 81 pounds per square inch, 81 PSI. So now we were able to do in just a few simple baby steps what most people require an app to do. But I think what's more important is we're actually able to understand how this conversion works and how we're able to take this little thing right here and convert square centimeters into square inches, or convert cubic centimeters into cubic inches. And I just think that's really cool right there to know how to do that and know what your app is actually doing. Next up, I'm going to show what we can do with this pressure. It's actually quite a bit. I mean, it's quite a bit of pressure. All right, I Googled the diameter of fire hoses. They gave between 1.5 and 2.5 inch diameter. I assume that's an internal diameter. They said some supply lines that go out to the trucks or something are up to 6 inches in diameter. But we'll just stick with the normal standard fire hose right there. Let's turn that diameter into an area, pi r squared. So we have to cut our diameter in half to get radius, square the radius. You'll get 5 inches squared. So 5 square inches is the area of this particular fire hose. So now let's take our area here of 5 square inches. 1 square inch equals 81 pounds because we're dealing with 81 PSI that we just calculated. 5 times 80 gives you about 400 pounds of force. And again, this is ignoring any internal resistance from flow. The narrower your pipes are, then the more that'll resist. But if you stick with some really wide pipes, I don't think it matters a whole lot. And this is also saying we have no pressure valves. And even more extreme, this is what would happen is if you hook your fire hose directly up to a water tower that's 200 feet tall. So 400 pounds, what that means is if you put a scale on your chest and have someone shoot a fire hose on it, or someone push on it or put a bunch of weight on it to where that scale, that bathroom scale, would weigh 400 pounds, yeah, it would crush you. You'd have to lay on the floor to have somebody put 400 pounds on your chest, or stand up against a wall or something. And if you had a fire hose that shot out that much pressure or that much force, yeah, you just take off like a rocket. I just remember there was a Mythbusters where they attached some fire hoses to a car and had those fire hoses point down to see if they could lift the car off the ground. But this is the math they would do to calculate how much force they're going to get. And this shows why you wouldn't want to connect a pipe or a hose directly to a 200-foot water tower.